Thanks for having me here. I'm actually I'm super excited about being on this stage specifically. So I'll have to tell you a story about why. So last September, I went to Monitorama Berlin. At the time, I was working on a company called Airplane. And it was two of us. Three of us working on it full time. We went through IC last year. And while I was there, I had some realizations about what we were doing and about monitoring in general. But the first thing I realized is that Berlin is totally awesome. You should go. And then the other thing was this. And I heard this quote months later when I was talking to Andrew about what we were building. But I realized this at Berlin, which is time series databases, open source time series databases, are kind of like a red-headed stepchild. They're just not getting love. And the other thing I realized was that there were a lot of talks and a lot of people talking about building complex infrastructures, how they move data around, how they store it. And that's the thing is, analytics and monitoring to me is a form of analytics, should be about analyzing and interpreting the data, not the infrastructure that you're building to store and process it. So Monitorama Berlin was the 19th and 20th of September. And I got back to New York on Sunday following, and then that Monday when I came into the office, I told Todd and John that I think we should be doing something different. And this is the first commit for InfluxDB, which was on September 26th. Now, Monitorama can't take all of the credit. We had actually been thinking about doing this for months. At the time, we were just thinking, oh, well, maybe we should open source our infrastructure so that other people can benefit from it and we can kind of build something around it. And in fact, on our YC application, our secondary idea that we listed was actually open source time series database. So the one thing I will give Monitorama credit for is giving me the courage to finally say, okay, maybe we should actually pivot. So we shut down Airplane, and now we're just working on InfluxDB. So thank you, Monitorama. All right, now let's talk about InfluxDB. And by the way, I just have all slides. If you want to ask questions, raise your hand, or actually just yell at me, and I will be happy to answer questions. So interrupt me if there's something specific you want to ask as I'm going through all this. So what is InfluxDB? It's an open source time series database. And a lot of people, when they hear that, they think, oh, is that like a round robin database, like Graphite or RRD? No, InfluxDB is not that. So then I was like, okay, maybe it's an open source time series metrics and events database. And I kept asking myself, why do people think time series means periodic measurements? Because in my mind, I always thought of time series as like a set of stock trades, right, which are discrete events. And then that's the actual time series, and then you perform functions and analysis on the time series, like getting the mean or getting the min or the max. So then I looked up time series and saw this definition: a series of values of a quantity obtained at successive times, often with equal intervals between them. So I guess like I've just been using time series wrong. So InfluxDB can actually store discrete events. It creates those equal intervals on the fly through aggregate functions. I was calling it a time series database because everything in InfluxDB is indexed by the series and the time series. But the point is, it's useful for analytics. And in my mind, this is like DevOps analytics, which most people here are interested in, but it's also useful for user analytics, business analytics, sensor data, all that kind of stuff. So now I guess I'm just going to call it an open source analytics database. Now the thing about a workshop. I didn't realize it was a workshop until like maybe a week or so ago. But I suck at live demoing things. So here's the workshop part. If you're on a Mac, do brew update, brew install InfluxDB. If you're not running homebrew, please do yourself a favor and start using it. If you're on Linux, there are RPM and Debian packages. If you are on Unix, I'm sorry, we do not have builds available. So go into the cloud and find a Linux box. OK, once you have it installed, point your browser to this, and then you will see this, a login screen. Default login is root. Then you will see this, a screen to create a database. You give it a name, you create it, and then you see it in the list. If you click that little explore link, you will see this, which is just a pretty ghetto interface for writing data in and doing ad hoc queries. All right, that's it for the workshop part. The rest of this is just like a talk. But I will cover the details about the API and stuff like that. So let's talk about the API. It's HTTP. And the reason we picked HTTP as the protocol for a database, which is an odd choice, because usually when you think databases, you think you want something really, really fast. But we wanted to optimize for usability. And the other thing is, we saw the whole ecosystem building around Graphite, which is awesome. And I think one of the reasons for that is because there's an HTTP API. Like developers find that easy to work with, and they can build tooling on top of it. You can access it directly from the browser. So we picked that as basically the first class thing. Here's how you do writes. You do a post. You specify, you see there in the URL, you have a database. Specify a username and password. You can do that through query strings, query parameters, or through basic auth. And then you pass it a JSON blob. Here's what the JSON blob might look like if you expand it out. It's an array of objects. Each object is a series, and you can post multiple points to a series. So here we have a series called CPU. We're feeding in the columns time, value, and host. The timestamp there is you might recognize as a seconds epoch, but under the covers, we store everything as a microsecond. So if you want higher precision, you can go milliseconds or microseconds. When you post it in, you just have to specify what precision timestamp you're writing in. And then the other thing you might notice from this that makes it different from, say, a round-robin database like Graphite or RRD is that you can have multiple columns, you can have multiple values, and the values aren't constrained to just being doubles or integers. You can have strings, you can have booleans, and you can define all this stuff on the fly. You don't have to define it ahead of time. And finally, the thing about the timestamp is if you don't feed it in, we will assign it for you automatically. Because like I said, everything is indexed on time. So queries, just do a get on /series, and you pass it a query parameter called q, which is a query string. So we created a SQL-ish query language for it. And this was actually something that we had learned while we were building Airplane. Airplane it was a SaaS product for like metrics and monitoring, and it had a REST API. And the thing is, I was talking to somebody once who was using it. I was trying to explain some concepts about how the API works. And at some point, he's like, oh yeah, that's just like a group by clause in SQL. I realized like we should try and piggyback on the knowledge that people already have. So if we can bastardize SQL, it will be easier for people to understand the query syntax and stuff like that. So this query is, give me all of the columns from the events series for the last hour. This one shows the fact that series names can have any character in them. You just need to wrap the series name in double quotes when you're doing a query against it. You can also do a select against regexes. So there are where clauses. You can do greater than, less than, equal to, or against a regex like this. You can specify the time range either as a string or as an epoch in seconds, milliseconds, or microseconds. And the thing about this query is it only scans the range of time that you specify. So whenever you're doing queries, if you specify a range of time, it's good to specify a range of time, a limited range of time, because it's more efficient. So we also wanted some tools for working with a lot of series. The thing about a SQL database is you're not going to have like 10,000 tables, right? But in a metrics database or a time series database, 10,000 metrics is almost nothing. Like most people who are doing metrics seriously have them in the hundreds of thousands or millions. So you can also do things like this where you say like, get the last data point from every series that matches stats.cpu. And we also support like downsampling on the fly through aggregate functions. So this was the thing I was talking about earlier, which is you take the series and you run some transform on it to get something else, which essentially is a summary of the series. So here we're getting the 90th percentile from response times in 10-minute buckets for the last day. So we get 24 times 6, or yeah, something, points out of it. We have a bunch of other aggregate functions, min, max, standard deviation, derivative for calculating rates, stuff like that. But we also have a thing so that this could be fast depending on how many data points you have in there. But if you have tons of data points, it could be slow. And if you have this on a dashboard, it's something that you want to come up quickly. So we have tools for doing continuous downsampling. And we call those continuous queries. So here's another example where we're getting the count from some series called events in 1-hour intervals, grouped by the time range and some page ID. And we're feeding this into new series called events dot, and then the square bracket page ID gets interpolated into whatever that is. So the into keyword basically tells InfluxDB, don't return a result for this, run it in the background on the cluster all the time. And basically what will happen is every hour, it will run this query for the last hour worth of data and write new series as a result of it.
Does it pick up historic data points as well?
Yes, it will backfill historic data points. Anything with a group by time interval will backfill based on that, it's something you'll have to work with also if you like create a continuous query and then you load a bunch of historical data. Like I said, this runs actually every hour, but it only runs for the last hour. So if you load historical data, the resulting continuous query series don't get updated. So what you'd want to do is delete those resulting series, then delete the continuous query and recreate it so all the data gets reloaded. So yeah, basically it would create a series that looks like this, right? We have a page ID of 67. We're selecting a count from events.67 for the last 7 days, and that's something that'll be very, very fast to return. You can also pair the continuous queries with regexes. So you can create basically like a standard that says, oh, anything that starts with stats, we're going to want the 90th percentile of. So just do that. We want 5-minute 90th percentiles. And here the colon series name gets interpolated into whatever the series is that's selected data from. So here, like, if we had percentiles per host. So with all the data in InfluxDB, the way you get performance out of it, the way you get faster queries is by denormalizing the data. So continuous queries is one example of that, those summaries. Let's look at a specific example here. So here we're looking at events. We say where the user ID equals 3 for the last hour. Now the thing is, events is going to be all user IDs mixed together, so it's going to scan through all of those which can be slow if you have a lot of events. So you can use continuous queries to basically fan out that data as it gets written into the database. So this just says create a new series per user. So you can still query against events for all of the users in aggregate, or then you'll be able to query against a specific user's event stream. So there are a bunch of tools for data collection. Multiple people have written collectd proxies. There probably are a couple of statsd backends. Carbon ingestion is there now, thanks to Dieter, who gave a talk on the first day of the conference, I think. And hopefully soon we'll have OpenTSDB ingestion as well. There are also some tools for visualization. So here's what the built-in UI looks like if you do a query. And as you can see, it tries to draw some basic graphs, but they aren't that pretty. It's good for like doing ad hoc exploration, but it's not good for like dashboards and stuff like that. Luckily, the next talk, you'll hear about Grafana, which has support for InfluxDB. Or you can always just grab your favorite charting library, pair that up with the JavaScript library, and kind of roll your own. Somebody was saying artisanal stuff is big in Portland, so artisanal analytics, maybe? Okay, so let's look at how all the data is organized in the data store. And once you see that, you can use that to frame like maybe how you should be storing things and what it's good for. So all of the data is organized into what's called a shard. And actually the idea of a shard, I came up with that basically from Logstash and Elasticsearch because they create a new index per day. So this is the same kind of thing. You have a shard is a contiguous block of time. You have a start time and an end time. And you have the servers that it lives on. So yeah, contiguous block. Now, in that example, the data for all series for a given time interval exist in that shard. Now, that's the default behavior. And every server knows about every shard that exists in the cluster. So let's jump through, good, looks okay. Let's jump through an example of a query. So here, we're counting values from some series called foo in 5-minute intervals. And we didn't specify times at all. So what that means is we're going to have to hit every single shard in the cluster to answer this query. So the query comes into server A, it distributes it out. Those computations get run locally where the server lives so that only the counts, the ticks, the 5-minute count ticks, get sent back up to server A, which then get collated together and sent back to the client. The key takeaway there is that group by times that are smaller than the shard size give you data locality, which is good for counts and percentiles and stuff like that. If you don't get data locality, it looks like this. So here, we're doing a 90th percentile from response times, and there's no group by time. So we're just saying what the 90th percentile is for all time. And essentially, when it queries the shards, they pipe all the raw data back over to server A, which then has to run the computation and send it back to the client. Actually, this is no longer true. We do a thing now where if we see it's a query that's going to pipe a lot of raw data back to the server that is issuing the query, we query the shards sequentially to guarantee this won't happen. And the other thing is that we evaluate the query and we only hit the shards that we need to hit to answer the question. So in this example, we're getting the counts just for the last 10 minutes. We look up, so the shards in the database, like I said, every server knows what shards exist. It's almost like a routing table instead of a hashing algorithm. It just says, okay, for this time range, what shards do I have to hit? I find the shard, I send the query there, and then I stream the result back. So shards are actually how we scale out. The configuration options look like this. You have the duration and some other some other things. So replication factor influences this. Basically, if your replication factor is 2, there will be 2 servers in there. It's just how many servers have a full copy of a given shard. So splitting durations into multiple shards is how we achieve write scalability. This thing here is basically how you achieve read scalability. You just create more copies of the shard and put them on more servers, and that will give you read scalability. Splitting durations into multiple shards gives you write scalability. So there was the split thing. So say split is 3, then when we create a shard, it looks something like this. The write comes in, we say, does the shard exist? If yes, do the normal thing. If not, call out to the RAF leader and create a shard create this duration of time. So if the split was 3, we create 3 separate shards. We perform the write, and then we're done. So how do we know which shard the data should live on? Basically, we look at the time bucket. N is the number of shards we have in that bucket. And the default behavior is we just hash the database in the series and figure out which N it falls on and write it there. So what that means is the default behavior says all the data for a given series will live in a specific shard. But you can override that by specifying a regex that just says, for any series that matches this regex, distribute the data randomly in the shards for that duration. So the implications of how all this stuff works is that if you're using the default behavior, you can get data locality on queries. But it means that writes will be hot for that shard for that series. So if you have a series that has a lot of data coming into it, it's gonna fall basically on one server or whatever servers own the copy of that shard. So if you have that situation, you want to use regexes, and that's how you can scale out writes. But the problem with that is to answer any query, we have to hit all the shards for that duration, pipe the raw data back, and then do the computation on the server that received the query. But the nice thing is that the rules for the replication factor and the split can change over time. Because like I said, it's more like a routing table, like a lookup table, than it is like a straight up hashing algorithm. So you can start with an RF of 1 and a split of 1, or an RF of, like, say 2 and a split of 1. And then as you start writing more and more data to it and you want to scale out, you can say, okay, we're taking in a lot more writes now, so we have to spread them across more servers, so we'll change the split to like 5 or 10 or whatever. So this idea actually is, if you notice the hashing algorithm, when we do hash to find out which shard data should go to, it's not a consistent hashing algorithm. So it's not like we can expand the number of shards for old data. But the thing is, in practice, that isn't really a problem because old shards are read hot, they're not write hot. So once it's no longer write hot, you don't really care what the split is. Okay, so the underlying storage, we use LevelDB as the storage engine. We create one LevelDB database per shard that exists. And what that means is when you drop a shard, you can do it very quickly and efficiently because essentially you're just like deleting all the LevelDB files. There's no like indexes or compaction that needs to be run or anything like that. So LevelDB is a log structured merge tree, and the data model is it's a key value store where the key space is ordered, which we take advantage of for time series. So this is what a key looks like for individual data points. It's 24 bytes. The first 8 bytes are an ID, which gets assigned to the database series and column. The next are the timestamp, which I said is a microsecond epoch. That also means you can only represent about, like 600 some odd years of time. So if you want to store data about ancient Rome, and now InfluxDB is probably not a good choice for you. And then the last bit is a sequence number, which is guaranteed to be unique in the cluster, because part of the sequence number is a unique server ID. And the reason we have sequence numbers is because of the fact that it's not a round-robin database, and we wanted to be able to support events. And oftentimes you can have events with the exact same timestamp in the same series. So looking at a couple of examples, say we have this point with a value, some string called context. Here we see, okay, value we'll say is the 1 column, and context is the number 2 column. So you see the timestamps are the same, and the sequence numbers are the same, which is how we know they're the same actual data point. Here's a different point, but the same timestamp. So it's just a higher sequence number. And the values look like this. We use protobuf for the intra-cluster communication protocol. It's TCP and protobuf. And we use protobuf to actually store the data in LevelDB. So as you can see, strings, doubles, booleans, ints. And protobuf actually does, for ints, it does variable length encoding. I'm not sure how big of an advantage that is because there's so much other data there. Combined with the fact that LevelDB compresses stuff anyway through Snappy. But yeah. Oh, and the other thing is we don't store Boolean or null values. So if you're feeding in points and you suddenly add a new column, that's fine for those new values. It won't do anything. It's not like in a SQL database where if you add a column, it does this crazy thing that can kill you if you have a table with many millions of rows. We don't care. Like, add columns all you want, and it doesn't matter. So what are the implications for the storage? Aggregate queries do range scans for the entire time range. Where clauses do range scans, which I mentioned. The other thing is queries that hit multiple columns will do a range scan per column that you're hitting. So somebody who was using it had like a situation where they had like 500 columns. They had a series and it had 500 columns. And sometimes they were doing queries where they're hitting all the columns and they're extremely slow. And they're like, why is it slow? I said, because of that. So the other thing is, based on the way it's built right now, because the first 3 digits of the sequence number are the server ID, it means right now you couldn't have any more than 999 servers in a cluster. But the truth is, right now, all the servers in a cluster participate in Raft consensus. So chances are you're probably not going to be able to run a cluster bigger than about 10 or 12 machines until we make some updates to that. All right. Wanted to talk about some coming soon stuff. And this is the stuff that I'd love to get feedback from people here about like what they think about these features and which ones are important to them, and if there are things that aren't in this list that should be. So documentation, hopefully I will get that done next week. The ability to specify metadata for different time series, like units and stuff like that. We'll probably be adding that pretty soon. We're seriously considering doing something like tags. If you've worked with OpenTSDB, it would work very much the same way it does in OpenTSDB. Considering adding in indexes, everything would still be indexed by time, but the way we're thinking about it is maybe giving you the ability to specify like 1 or more columns that a series should be indexed by so that you can do quick lookups on that. Then another thought is automatic downsampling. Right now, we're pushing everybody to use continuous queries for all the downsampling, but it seems like such a common use case that we may add something in there to do it automatically for you in certain instances. Binary protocol is definitely coming. Multiple people have already asked about that. And once we do that, then we can do pub sub, which I would love to get done. The idea for this is it work like this. So any query you can issue, you just say into subscription and you act like it's a function call, and then that client will just get that data stream to it. So here, like, it would filter out anything that isn't server A, or anything that is server A, and send it down to the client. And for the second query, the client would just get a tick once a minute for that percentile. And then one other idea was when you do this query, each subscription would have a unique ID that it gets assigned, so that you could have other clients call subscription with that ID, and then it would end up load balancing the data for that subscription across all the connected clients. We'd like to add custom functions. So originally we thought we would use Lua, but it seems that not very many people want to write Lua, so now we're thinking JavaScript, although I'm curious if you had custom functions. So the idea behind it is you define code in either Lua or JavaScript, you insert it in the cluster, and then from that point forward, you can just call it by name in the query language. So show of hands, who would prefer Lua?
Way more performant.
That's bigger than I thought it would be. Who would prefer JavaScript? Whoa.
One of each.
Who would like one of them?
Who would want both?
If you want performance, you want strict types, a list of an object. JavaScript sucks on typing.
So
Which means for heavy set functions, it will just tear you apart.
you also won't have integers.
Yeah.
Everything's float.
You want equality to work.
One is not
Just use
one.
triple equals.
How about Go?
The problem with using Go for custom functions is that you need to rebuild the binary and redeploy it to all the servers. You can't dynamically link in new Go code, which they may be adding that at some point in the future, but that's so far off probably. Huh?
I had a question about your prior slide about splitting things off.
Yeah.
So if I have a lot of data that I don't use too often, but a little bit of data that I use all the time, is there some value in partitioning by databases? And at what point, in terms of size, do I need to think about that? I know you got to think about the numbers, or should I just throw it in the same?
Right. So the question was, if I have some data that I use all the time and some data that I use very infrequently, is there some special way I should be thinking about partitioning my data in Influx? Should I be creating databases or something like that? So actually, one thing I didn't cover in here is that there are two separate shard spaces. We're calling them right now short-term and long-term. We're going to be changing that so that you can have n shard spaces where you can name them. And the idea is, right now, the way it works is if a time series begins with a capital letter, it will be written into the long-term shard space. And the different shard spaces can have totally different durations. So right now, the default is short terms are 7 days, long terms are 30 days. And the idea behind that, behind creating n shard spaces, is that we want to have it so that you can automatically feed like high precision data, which is recent, into one shard space and very quickly and efficiently drop that old high precision data, and then have downsampling that runs continuously that feeds into some other shard space where you want to keep it around for a long time, right? Because most of the time when you're looking at high precision data, you care about high precision in the near term for things that were very recent, but longer term you care about trends and downsampled stuff, unless you have lots of money and keep everything forever.
For custom functions, somebody mentioned Python earlier, like
Yep.
for NumPy, SciPy, Pandas, also R too. Interesting.
I have no idea how you would embed Python or R into it. So one other idea instead of custom functions is to just do a thing where we create like a binary like protocol, like a protobuf protocol or something like that, and have it work kind of like streaming does in Hadoop, except for something that doesn't suck, ideally. So then the idea would be like you could write it in any language you choose, and there would be an easy way to just get that deployed into the cluster, and you could do queries where you pipe it into one of those running processes. But if we do that, that's definitely like further out on the timeline. So yeah, I mean, the best situation would be people can write code in whatever language they want to write code in. We would love to support that. The easiest and most expedient thing would probably be Lua. But I was actually very surprised that as many people raised their hands for Lua as did. I'm curious what it would be like at a different conference.
That might have been more of a negative vote for JavaScript than a positive vote for Lua.
Are we your target audience?
Are we your target audience? Yes. DevOps is definitely one of our target use cases. That's basically what it was born from. Airplane was basically, for the most part, storing DevOps style data and monitoring data. So yes, DevOps and monitoring is definitely a target use case for us, but we also have other things like user analytics and stuff like that, which you may or may not care about. So rack-aware sharding and querying. Rack-aware is nice because even if you don't run racks, like if you're on EC2, you treat each AZ as a rack. That way you can get fault tolerance across AZs easily. Multi-data center replication. We want to do both push and bidirectional. Originally, when I was thinking about multi-data center replication, I thought bidirectional was really the only use case. Like generally, you're like creating a mirror of your data. And then somebody told me that they had a use case where they had regional data centers around the world, and they wanted to be able to query the data locally there quickly, but they wanted them all to push their data up to one massive data center somewhere. So that's something we want to do. But it's ready now. We are running some clusters for people. Actually, by show of hands, is there anybody in the audience who is actually running InfluxDB right now? Thank you. I love all of you. So yeah, basically we're here to help, and I would love to hear feedback from everybody about what we're building, what we need to build, all that kind of stuff. And it looks like I have 6.5 minutes for questions. Yes?
Do you have consistency guarantees for when like you're forced to rebuild data?
The question was, do we have consistency guarantees about when you're forced to rebuild data? So we don't have tunable consistency right now. When a write comes in to the cluster, the request gets assigned a sequence number, and all the data points within the request get assigned timestamps and sequence numbers themselves if they don't have them. And then it gets logged to a write-ahead log that we created. As soon as it's logged to the wall, it returns a success. Now, it's a configuration option to say whether or not you should fsync on every write to the wall, or fsync after n, or let the operating system handle it. Obviously, you'll get much better performance if you don't fsync on every single write. Once it's done that, then it will attempt to replicate the data to whichever servers in the cluster have copies of the shard that owns that data. And it will just keep trying until. Now, there is one problem right now where if a write happens and say the data gets replicated to one server and then the server that took the write dies and doesn't come back, it doesn't get replicated at the moment to the second server. We'll be fixing that soon. So basically, like, people keep telling me like, oh, it's a distributed database. You should have Kyle, tear into it. And I'm like, no, Kyle would be way too mean to us right now. I'll beg Kyle to tear into it when I think we're ready, and we're not there yet. Yeah. Can you do bulk delete of data points? Oh, bulk editing?
Editing or deleting.
Bulk editing or deleting. Deleting, oh yeah, I didn't even show that query. You can say delete from some series and give it a time range. That isn't very efficient right now, basically because of the way LevelDB works. Essentially, it'll do a range scan for all that, do deletes, and then force a compaction. LevelDB, when you do deletes, it doesn't actually delete the data. It basically creates a tombstone record, and then later on, when you run a compaction, it clears that up and frees up the disk space. So that's actually quite slow. The best way to delete data at this point is to partition things into the shard spaces and then just drop the shard. Bulk editing. Are you thinking of the case of like you're reloading some old data or something like that, or?
Data, need to change the label on something. Maybe one metric was too verbose, too voluminous, you delete it.
So you can actually update data points. If you specify when you write data in a time and a sequence number, that will basically just update. If there's something already there, it will just update what's there. We're not optimizing for updates though, and I don't know. I don't think we're ever going to provide guarantees about multiple writers trying to update the same point, just because it's not. We don't want to worry about that use case. There are other databases, distributed databases, that are well designed for that use case. We want to design for the use case of you're either bulk loading a lot of historical data, or you're loading in new data, or you're dropping some massive chunk of old data. Like it's the analytics use case, right? Where it's essentially like you're always appending, you're never updating. Yeah.
Say you've got a single instance and you set it to shard like 5 week or something or other. What's the process for going to multiple instances?
So the question was, say you have a single instance and you set it to shard by like a week. What's the process for going to multiple instances? When you start up a server, there's a configuration option called seed servers. So you just pointed it into a server, an existing server in a cluster. When new shards get created, that server will get those shards. Sometime in the next, hopefully 4 weeks, we'll add functionality to copy shards between servers really easily. You can't, right now, the only way you do it, it's like, actually you couldn't even, you can manually copy the data, but I don't think we've even exposed an endpoint in the API to tell the cluster that the data now lives on another server. So we will have something soon, but in the short term, it's essentially add servers to the cluster. For the servers, update your replication factor and potentially your split if it's writes that's causing you to want to expand, like your how many writes you're doing. And then when new shards get created, they'll get created under those rules.
And similar story for availability.
Similar story for availability?
Yeah, rather than just writes.
Yeah, exactly, for availability. Yeah, so we're running a couple of clusters where there are just 2 machines, and the only reason we're running 2 is for high availability. Yeah, and those run hot. You can write to either server if you're running in that configuration. In the back?
Did you ever consider Cassandra, and if so, what made you go against it?
So the question was, did I ever consider Cassandra, and if so, what made me go against it? I've built 2 time series databases on top of Cassandra, and I know other people have as well. Many people have. In 2011, I worked at a fintech startup, and we were replacing some old school proprietary like ticker plant with basically Scala web services on top of Cassandra. So there were a couple of reasons why, and the original version of the Airplane API was built on top of Cassandra. There were 2 motivating factors that caused us to want to use an embedded database and build our own distributed system. One was, at the time, we thought we wanted to do on-premise deployments of Airplane eventually. And to do an on-prem deployment, it's really tough to tell somebody, hey, spin up this Cassandra cluster and run these web services and do all this other stuff, and then hate yourself. So we just wanted to be able to like hand them a binary and let them run with that, which I think has worked out pretty well for this as an open source project because it's so simple to get running. I've definitely heard people say that they started using Influx because Graphite was too much of a pain to install. So, and that was one thing we tried to learn from MongoDB. Say what you will about MongoDB, but they got developer usability right very early on. Like they made it super easy to get going. And then the other one was, sorry, 1 second. The other one was with Cassandra, you don't get data locality. Whenever you want to run a query over raw data, you have to pipe all the data back to the server, do your computation, and then run it back. So we wanted to be able to get data locality. That was the lesson from Hadoop, right? Ship the code to where the data lives, not the other way around. Yeah. I'm out of time. Thank you.